first thing we'll look at is the twitch. Okay, the twitch. And the twitch is the phenomenon that if you took a piece of muscle, let's say you took a researcher was in a lab, she was studying muscle, and you took a piece of muscle, suspended it, right? And you stimulate it with enough force to mimic an action potential, like a motor neuron would. What you would see is that the muscle would generate force or tension, and then that force would fall to zero very quickly. Okay, so it would essentially contract very quickly and then relax. And that is called twitch, muscle twitch. Okay. So twitch is a mechanical force that is generated in a muscle as a result of an action. Now this can be on the level of the sarcomere or the myofibril. This can be on the level of the muscle fiber, a single muscle cell. This can be at the level of a motor unit, which is a motor neuron and all the fibers it's innervating, or this can be at the level of the entire muscle body. Okay. So we said that all of those structures shorten to bring about shortening of the muscle fiber, and the muscle fiber shortens, that brings about shortening of the fascicle, shortening of the body, and so on and so forth. So you can see a twitch on each of those levels. All right. Okay. Now, when we talk about a twitch has several phases or several periods. There are 3 phases to a twitch. And we actually plot those out on this graph. So this graph is representing time, right, on the x-axis, and then the amount of tension or force that's produced by that muscle on the y-axis. Okay? So time versus tension. And when you first stimulate that muscle body with an action potential, there's going to be a little bit of a lag time between the stimulus and the beginning of contraction. There's going to be a time when there is no force generated. Why? There are not cross-bridge cycles happening yet. This is called a latent period. Okay? This is the time that's allowing for excitation, contraction, coupling to happen. So if you remember, we talked about excitation, contraction, coupling. We said that a muscle was stimulated by a motor neuron, an action potential or an end potential was generated that had to propagate down the T-tubules and had to open up those calcium channels and calcium move from the sarcoplasmic reticulum into the cytosol. So in this brief period, a couple milliseconds, that is the water bath, that is happening. And so we do not have cross-bridge cycling yet, and so we do not have force generated. Okay, that's the latent period. Then you will see that the force generated will rise very quickly. That's the second phase. This is the contraction phase of muscle. Okay. This can be anywhere from 10 to 100 milliseconds, depending on the location of the muscle and the type of fibers. We're going to look at fiber types later on, but the type of fibers present in that muscle. And during this part of the twitch, we have active cross-bridge cycling. Okay. So calcium has entered the cytosol, interact with those troponin molecules. That's going to make those tropomyosin sites, those myosin binding sites available, and active cross-bridge cycling is occurring. Okay, so as we see, force or tension is generated as that sarcomere shortens. Then there is the relaxation phase. Okay? And that is where, again, force drops off. This phase is much slower. It's the longest phase of the twitch. Okay, here you can see the force slowly drops off as that muscle relaxes to its original resting length. Okay. And this is where calcium is now leaving the cytosol. And so cross-bridge cycles are being broken, and we do not have as much calcium floating in the cytosol as during the contraction. So these are the phases of a twitch or the phases of a muscle contraction. Now, when we look at a twitch, there are 2 types. So our muscle can contract in 2 different ways. There's an isometric contraction and an isotonic contraction. But what's important to understand with these two types of contraction is that there are two elements to a muscle. There's a contractile element, okay? And let's understand this before we get into what the two types are. There's a contractile element of the muscle, that's the sarcomeres. That's the myofibrils, that's the meaty part of the muscle. That's the muscle body, or the muscle belly. And that is actively shortening. And then there is the series elastic elements, okay? That is essentially the tendon. That's connective tissue of the tendon, that's at the outer boundaries of the muscle. That is not contractile. That is not actively shortening. That does not have any sarcomeres. Okay, so there's a contractile element, and essentially what is a non-contractile element? It's called the series elastic element. And it's basically the tendon at the ends of that. Now there's a force that can be generated from my muscle contracting. And this is where we start to look at the mechanics of muscle. Okay? If I'm trying to pick up this bottle, my muscle needs to generate some force here. Okay? And in order to do so, I will move the bottle. Okay? The force that's generated here is also called a tension. And that needs to overcome the weight of this bottle, which is called the load. Okay, I'll say that again. I'm trying to move this bottle. My muscle needs to generate some force or some tension. Okay? And when it does so, and it overcomes the weight of this bottle, it will have lifted the bottle. This is called the load that is overcome from the tension generated by my muscle. Okay? So the tension generated here, the load is the weight of the body. Okay, that's going to have a lot to do with what we're going to talk about later on. So the first style or type of twitch is the isometric twitch. Isometric twitch contraction. And as the name here implies, iso means same or constant, metric meaning length, right? The length of the muscle remains the same for an isometric contraction. The muscle does not shorten. That's going to be very important. This is when the load, I'm trying to lift that bottle again, the load is too heavy. So if I'm trying to lift this bottle, right, let's say it was really heavy, I would generate some tension trying to pick it up, but I would never actually move it from the table, and that muscle would never actually shorten. Okay, I would still generate tension in my attempt to pick it up. Okay, that's where the load is greater than the tension produced. If you're trying to lift an 80-pound dumbbell, and then generate some tension as you try to pick it up. Your muscles will tighten, but they will not shorten. Remember, you need that muscle to shorten to move across that bone. So if the muscle never shortens, you never pick up that load. And that's because it's too heavy. Now what's happening here is the contractile elements are generating tension. So remember we said the contractile elements is the body or the belly of the muscle. Okay, it's generating tension, so it's contracting. You can see here. Okay, it's contracting or tightening up. But the series elastic element, so the tendon, is going to extend in such a way that it cancels out the contraction of the muscle. I'll say that again. So the stretching of the tendon, right, this is the tendon attached here. And you can see how it's a little bit longer here than in this one. That's because the tendon has some give. It's going to stretch as that muscle then shortens, and it's going to cancel out so that the muscle never actually moves. Okay? So in this first image, we had that muscle in its relaxed state. We stimulated it. Okay? It's shortened here. You can see it swell up as the sarcomeres shorten. But then the tendons stretch, or the series elastic elements stretch, and so we don't notice a difference in the entire length of the muscle. The muscle does not contract, essentially. Okay? And that's because we did not overcome the load. The load is too heavy. And that's isometric. Let's look at isotonic. Isotonic contraction. And iso, again, means same. Tonic means tension. Here, we we do generate enough tension to move the load. And at the point where we do have enough tension to move the load, that tension is going to remain constant for a little bit while the muscle contracts, and then it will drop off. Let's repeat that again. So here, we are generating enough tension. So if we compare these two images here, we have our resting muscle. Okay, it's suspended. It's attached to a load. And now, this muscle can generate enough force to lift this load. So when we stimulate this muscle, it will contract, okay, and the load will move. This is sort of a lever here. The load will move. Why? Because we have generated enough force, enough tension in the muscle body to lift that load, and so the muscle shortens and the load moves. Okay? Let's look at these graphs. So in this graph, this was the isometric. I went back a slide. We had that tension rising here. And because it was never enough to actually overcome the load, it's just going to rise until it drops off. Okay. It's just going to rise, it'll twitch, and then it'll relax. It'll drop off. When we are able to overcome the load, this graph is going to flatten at the top, or it's going to plateau. Why? Because at this point, we've generated enough tension here, at this point, to overcome this load, and we're going to have a constant, smooth tension generated here, and then we drop off. Okay, it's not going to continue rising, because at this point, we can overcome that load, so we don't need any more tension. We just need to keep the tension constant as that muscle contracts, and then it drops off. So for an isotonic contraction, we have a flattened or plateaued graph, and that is representing the constant tension. If you get to a place where you have enough tension to generate the load, you're going to keep it nice and steady, and then it will drop off. Okay, so this graph sort of compares those two, and we'll go through it. So we have our four sort of simulations at the top here. We have different loads attached to this muscle. We have a 5-gram load, 10 gram, 15 grams, 20 grams. Let's say that the muscle that we're talking about here can only lift 17 grams. Okay. Physically feasible, we can only lift that amount of weight. We have our latent phase here, right? This is before excitation, contraction, coupling has completed, and then we start to generate some tension. And then at this point, right, we have 5 grams, we have generated enough force to lift this 5-gram load. So we're not going to generate any more force. We're just going to have a nice slow contraction at constant tension, and then we drop off. Right? That's your 5-gram load. Let's look at a 10-gram load. Similar. You have your latent phase, contraction begins. Now this time, this is a little bit heavier. We're going to keep going with the tension until we get to an area where we can overcome this 10-gram load. Okay, so we're going to contract a little bit further than if we were lifting a 5-gram load. And at the point where we can comfortably overcome this load, the tension remains the same, and then it drops off. Let's look at a 15-gram load. Similar phenomenon. We're going to generate enough force to move a 15-gram load. It's going to be more than these two scenarios, and then we're going to have a very brief contraction because this load is heavier, and then we're going to drop off. Okay. Let's try to lift a 20-gram load with a muscle that can only lift 17 grams. We are going to generate force, right? Generating force here. Generating force here. This muscle never actually shortens. So we're just going to get to the maximum that we can physically go to, and then we will drop off. Okay, it's never going to get to 20. At 20, it would have flattened off. But physically, feasibly, this muscle cannot lift 20 grams. So when it gets to 70, which is the maximum load that it can bear, it will just drop off. And as you can see, the graph does not have that plateau top because the muscle does not contract. The muscle is never contracted at a constant tension. Okay, so these are your isotonic contractions, and this is your isometric contraction. Okay? Here, we can lift the load. Here, we cannot lift the load.